I'm Dugas. This screencast is about solving polynomial equations through different techniques of factoring and some combinations. So let's look at a technique, and we're adding on to some of the techniques we already have, like greatest common factors, difference of squares, and things like that. So here's a new technique, factoring a sum and difference of cubes, things raised to the third degree. A sum of two cubes follows the pattern a cubed plus b cubed, and that's what we're looking for, a perfect cube on either side of an addition. And that's equal to a plus b, the quantity, times a squared minus ab plus b squared. A difference of two cubes follows a similar pattern, a cubed minus b cubed, and that is going to be a minus b times a squared plus ab plus b squared. So notice for the sum, the first term is added, and then we have one of the middle terms is negative, and then in a difference, the first term is a subtraction, and then it's multiplied by everything that's positive because the negative gets distributed to everything. So we're looking for situations where perfect cubes are occurring. So let's look at an example and a non-example. Turns out this one's a non-example. So x to the third, certainly that is a perfect cube of x. 400, however, is not a perfect cube. Therefore, this is a prime polynomial. A prime polynomial is a polynomial that cannot be factored, just like 5 is a prime number because it does not factor other than with 1. The same thing's true for polynomials. Now, if we looked at 24x to the fifth plus 3x squared y to the third, the first thing we want to try to do is look for greatest common factors. Always try to do that first when you're factoring. It usually takes things and makes them simpler. In this case, both 24x to the fifth and 3x squared y to the third have a 3 in common, because 24, after all, 3 is a factor of 24. And they also have an x to the second in common. So if we pull out that 3x to the second common factor, what we're left with is 8x to the third in the first term and y to the third in the second term. So this is already somewhat factored. But we can continue the factoring because 8x to the third plus y to the third is a sum of perfect cubes. Because 8x to the third is equal to 2x, the quantity raised to the third power. So we can rewrite 8x to the third plus y to the third as quantity 2x raised to the third power because the 2 gets distributed to the third power, becomes 8. And of course y to the third power. If we use 2x as the a term and y as the b term, we can use that formula, the sum of perfect cubes. So it becomes all of, this is a plus b times a squared minus ab plus b squared. That's that formula for the sum of perfect cubes. Now we still have to put in at the end that greatest common factor, the 3x squared, but when we take what we just did and put it together with the 3x squared, we have our factored solution. Let's look at an example of factoring by grouping, which we're going to want to do factoring by grouping whenever we have 4 or more terms. We want to look at that as a possibility. First, look for a greatest common factor. Well, there isn't any in all 4 of these terms, but if we take any 2 of them, for example, the first 2 and the last 2, and then try to group them, we can find a common factor. In fact, so we're taking that first group and that second group together, and we can pull out an x squared out of the first 2 terms, that first group. When we do that, we get x squared times the quantity x plus 5. Okay? And then in the second group, if we take out a negative 2, then we're left with negative 2 times the quantity x plus 5. Be careful with negatives, of course, as always. Well, now you notice both of these groups have an x plus 5 in common. So we can take the distributive property in reverse, and so this becomes x squared minus 2 all times x plus 5. And so together, this becomes our factored form. And that makes it easier to solve something. So if we had this all equal to 0, for example, it'd be a lot easier to solve this now because we would just look at the zero product property. Either the x squared minus 2 is equal to 0 or the x plus 5 is equal to 0. And so if we were solving this, the solutions would be the solution to the first part, which would be plus or minus the square root of 2, and the solution to the second part, which is x equals negative 5. So let's look at a combination of techniques, because typically that's what happens. Okay, so here's 6 terms. So we definitely want to look at possibility of grouping these things together. Well, if you look at this carefully, the first 3 terms have a y to the third in them. The last 3 terms have a z to the third in them. So I'm already thinking in this one, there could be some sort of perfect cubes, and I've got grouping to do. But we're going to do the grouping first. When we group it into 2 groups, we can see that there's that y cubed term in multiple places, and then there's the z cubed terms. So each of those 2 groups is going to have that common factor. We pull out the y to the third. Out of these first 3 terms, when we get x squared minus 3x plus 2, when we pull out the y to the third from those 3 terms. Similarly, when we pull out the z to the third, out of these 3 terms, we're left with x squared minus 3x plus 2. Voila, these have something in common, an x squared minus 3x plus 2. So what we can do now is use the distributive property in reverse, and we get a y to the third plus z to the third. Oh, there's that sum of perfect cubes. And then we have this quadratic. Well, both of these things can factor even further. So not only do we have a sum of cubes in this first part, following that pattern we talked about, a plus b times a squared minus ab plus b squared, the sum of cubes. But then, turns out this other part is going to factor as well. So if we go back to previous screencasts on our x factor, we need things that multiply to give us positive 2 and add to give us negative 3. Well, if we use the numbers minus 2 and minus 1, we will achieve that objective. So therefore, all of that quadratic factors to x minus 2 times x minus 1. So we put them all together in a giant train of polynomials, and it is factored. The final technique we're going to look at in this screencast is using what's called a quadratic form. Something doesn't have to be to the second power by itself to be a quadratic. It can follow a form if we can do a substitution and wind up having something to the second power. And what we're looking for is a form a times u squared plus b times u plus c. And instead of u being just x, u is some sort of an expression of x. An example may be more helpful. So if I look at something like this, 12x to the 6th plus 4x to the 3rd plus 1, it doesn't appear to be quadratic at all. In fact, it's a 6th degree polynomial expression. However, if I let u be equal to 2x to the 3rd power, and the reason I chose a 2 is because both of these have a factor of 2 in them, and they both have an x to the 3rd in them. So it's kind of grouping these first 2 terms. But if I let u be 2x to the 3rd, then this becomes, if I take 2x to the 3rd out of this becomes 3 times 2x to the 3rd raised to the 2nd power, because 2x to the 3rd raised to the 2nd power is 4x to the 6th. And of course, 4x to the 6th times 3 is going to be 12x to the 6th. So that kind of takes care of that first term. And then the second term, 2 times 2x to the 3rd becomes 4x to the 3rd. So this begins to follow that pattern. 3 times u squared plus 2 times u plus 1, where u is equal to 2x to the 3rd. And that is what we would factor as a quadratic. And then we would go back in the end and resubstitute in for x. If we have something x to the 4th minus 29x squared plus 100 equals 0, there's a polynomial, and we want to find out what x values make this true. If I'm looking at my first 2 terms here, I've got a 4th degree and a 2nd degree, so this is a really good candidate for that. So if I let u be equal to x squared, I can rewrite this as u squared minus 29 times u plus 100 equals 0 by letting u equals x squared. That's the key to this. It's called substitution. We're substituting everywhere we see an x squared, we're putting in a u, and now it's in a quadratic form which you may already be familiar with how to solve. Now 100 has a lot of factors, but if we use the X technique, I'm looking for numbers that multiply to give me 100 and add together to give me negative 29. So we're going to go do the short version here. Negative 25 and negative 4 work. So this is rewritten then as u minus 25 times u minus 4 equals 0. Well, using the zero product property, u is either 25 or u is equal to 4. Now, that doesn't mean that 25 and 4 are the solutions to that. It is not, but it gets us one more step on the road. At the end, we have to resubstitute back in for x. Everywhere we see a u, we're going to put in an x squared now because we have said that u and x squared are interchangeable. To be able to solve for x squared equals 25 or x squared equals 4, both of which have their own solutions. X is either plus or minus the square root of 25 or plus or minus the square root of 4, meaning that there are 4 different solutions to this, which kind of makes sense. In the end, it is a 4th degree equation. It could have as many as 4 real zeros, and in fact it does. Positive and negative 5 and positive and negative 2. As always, check your answers, but that's a situation where a quadratic form will help us to factor and then solve. So this screencast covered analytic techniques for solving polynomial functions through factoring, primarily focused on the sum and difference of cubes and quadratic form, as well as factoring by grouping.